Okay, so let's take a look today at this topic, this IB topic called resource management and what that means. Okay, so let's take a look at what the curriculum says. The curriculum says identify resources that need to be managed within a computer system. Example, primary memory, secondary memory, processor speed, bandwidth, screen resolution, disk storage, sound processor, graphics processor. So basically what they're saying is if the computer has to manage all these resources, identify some of them. Like what does a computer need to manage, right? And it's a lot of stuff. Next point, evaluate the resources available in a variety of computer systems. These could include, so here we want to think about different types of computer systems other than, say, these PCs in front of you, right? So for that, we could be talking about cell phone technology, tablet technology. We could be talking about laptops versus desktops. We could be talking about mainframe computers, okay? Even things, simple computing devices, like, say, a digital camera, which doesn't have the kind of user interface as, say, a tablet. Those are the types of things it's talking about. Different computer, notice it uses the word system, not computer device. Identify the range, limitations of a range of resources in a specified computer system. So this is talking about things like single processor versus dual processor, how it can render 3D graphics, etc., or quad processors and stuff like that. Describe the possible problems resulting from the limitations in the resources in a computer system. So for example, user time is wasted if the primary memory is too small or the processor speed is inadequate. So basically this is just talking about what would happen if the computer is limited in what it could do, okay? Then it says explain the role of the operating system in terms of managing memory, peripherals, and hardware. Outline the operating system resource management techniques, including scheduling, policies, multitasking, etc. Discuss the advantage of producing a dedicated operating system for a device. Okay, so this would be if you're building some sort of digital camera, what would be the benefit of you writing the operating system for just that little device, okay, versus using sort of flexible operating systems. So for example, with cell phones, a lot of cell phones use the Droid operating system, right, the Android operating system, versus, say, Apple, which uses its own operating system. What's the advantage of making your own operating system versus using somebody else's? Outline how an operating system hides the complexity of hardware from users and applications. This is the idea that the operating system makes stuff easy for people versus the fact that some complicated technology is going on behind the scenes. Okay, so let's dive in. Those are the curriculum points. So what does an operating system do, right? Well, programmers, as they started to develop software, realized that they could make tools to help program, right? Not just tools to solve the problem, but tools to help with their programming. And you guys know this as programmers. You've made tools that, I mean, the second you learned about methods, you started doing that. Then the second you started learning about classes, you started making classes that held methods that would be useful tools for solving problems, okay? So if you think of software divided into the two categories of apps, application software, and system software, or operating system software, often shortened to OS, this separates the two, right? So the operating system is software to help run the application software, or the OS runs the apps. Apps address specific problems, like word processing, or surfing the net, or playing a game. They are specific to a problem, whereas system software manages the app software, as well as managing the hardware of the system, okay? So the operating system is the core. So here's the little simple diagram that sort of explains it. The human users interact with apps, right? When you use Word, you're interacting with Word. Human users also interact with the operating system. When they turn on the computer and they log into Windows, they're using the operating system. The operating system interacts with the apps. However, it is the operating system that interacts with the other system software, like the actual hardware of the system, which is even further down here, Other system software could include software like built-in software like BIOS software that's burned right into the hardware itself, okay? Or some little software that's built into a graphics card to make graphics. So that's a simple kind of a diagram that explains what's going on. So the humans never directly interact with hardware, never. The humans never directly interact with system software. It goes through the operating system. So the operating system is in charge, right? Okay. So if we think about pulling away from your traditional computers and going to computing devices, like for example a cell phone, same sort of system applies. On a cell phone you have an OS, an operating system, that you, the user, interact with. That OS will interact with the hardware, okay? Now let's go simpler than even a cell phone. Let's go with something that's a real simple computing device. Give me an example of something that's super simple computing device. How about a washing machine? Okay, I just bought a new washing machine, right? So on my washing machine, it doesn't have dials anymore. It's got buttons, right? So when I want to run a load on my washing machine, I have to press the buttons to program it to run, like for example, a hot load versus a cold load, and the spin cycle. All that stuff is in there. Now I'm not interacting with the hardware. I'm interacting with an operating system built for that piece of hardware, okay? So the operating system takes control of the hardware for you, okay? Hardware usually has a set of simple startup instructions that is locked into the hardware, often called the bootstrap instructions or boot software, okay? That's where it comes from, by the way. They used to have this term that you'd pick yourself up by your bootstraps. I guess in old like Western times, the boots had these big straps on them, and if you fell down, you could actually use the straps to help pick yourself up. So they said, oh, he's just bootstrapping himself. And that got shortened to just booting, and then booting became picked up popular by the computer industry to just mean the startup process, okay? So modern operating systems also are better at managing all this stuff. So they'll do things like manage your memory so that you can do two tasks at once. So if you pull back to my washing machine, it doesn't have that, right? It's not going to put that in there. But if you go up to, say, a cell phone or a computing device like a tablet or a PC, it's going to have that. It's going to have the ability to do more than one thing at once, multitask, okay? A process is an app. So an OS runs, when it says it's running a process, it's running an app. So these words get a little interchanged with one another. All right. So the OS manages the processes, process management, okay? Sometimes a process or an app needs to be scheduled. So for example, you could have an app that runs a backup on your computer, and you've scheduled it for a certain time. Sometimes a process needs to be interrupted. Okay? So for example, you're typing a letter and all of a sudden Skype appears on your screen. It has interrupted one app with another, right? Or one process. So this whole process is called CPU scheduling, where the CPU and the OS schedule and manage which apps get put into what order and when interrupts take place. Okay? So this is all part of that execution cycle that we talked about, the machine instruction cycle. At certain points, it sets up the schedule in that cycle so that it can determine when interrupts take place. If you go with a simpler device, like say my washing machine, it's not going to have a complex scheduling system. It's going to have a very simple scheduling system. But the more complex the hardware becomes, obviously the more complex the software needs to become to manage that. So this relates to something called timeshares on the computer, where it basically, like a big schedule I'd have up here, like this schedule actually, I block out what's happening at what times, okay? And this is complicated for the computer because it has to think about multitasking, multi-threading, multi-programming. With difficult hardware like multiple processors, quad-core processors, it has to think about, well, what's processes am I giving to that processor? Which processes am I giving to that processor? Which things am I giving to my GPU that's over on my graphics card? It has to manage all that. It has to be a very good boss at delegating who gets what job. Okay? All right. Now, if we think back to mainframe computings, you don't see those much anymore, but they still exist. A mainframe computer is one giant computer, usually housed in one sort of room. And then everyone just connects to that computer. So again, imagine that we didn't have 30 computers in here. We just had 30 screens and 30 keyboards. And over here at my desk, I had one big computer. What would be the advantage of that? Well, one of the advantages of having a mainframe computer is if I upgrade my Microsoft Word, all of you get the upgrade, right? Whereas in this room, if I want to upgrade Microsoft Word, I got to go to each individual of the 30 computers. Okay? So if I upgrade the mainframe, everybody gets the advantage of it. What's the disadvantages of having a mainframe? Yeah, you get a virus on that one, everyone gets it. It's expensive because obviously in order to do this, you need a really powerful computer. And it might not actually be powerful enough for what you guys want to do with it. So let's say all of us in here want to all run like video editing software and play a game and cruise the internet all at the same time. And 30 of you are trying to do that off the mainframe. That's a lot of work for the mainframe to do. You guys might notice it slowing down. Whereas if you all have your own computer, you might be able to manage that on yourself because you don't have to worry about everybody else. So there's always advantages and disadvantages to these systems, right? Mainframes often exist in things like military organizations and stuff like that because they're very secure. You can really up the security on there. But what happened is mainframes became less popular when personal computers, and I'm going to say that which includes the Mac is also a personal computer, started incorporating more networking technologies, right? So that the computers could have the advantage of being personal, but also pick up the same advantage of mainframes in they could connect and communicate quite well, okay? And that's what's kind of being covered on this slide here, is this idea that we saw a bit of a shift from mainframe computers to personal computers, okay? Or mini computers, it was sometimes called that, where that wasn't the case anymore, okay? Now the original PCs were designed for single use by a single person. They weren't designed that different people could log in and use the computer in different ways, right? Again, we tend to sometimes think that way. When you buy a new laptop, you think, I'm the only one that's ever going to use this. But wait till you guys get older like me, when you have like one computer in a household, and you want like, you know, your young children to not necessarily have access to some stuff, you often create logins and you create profiles, just like we have here in the school, where different users can use the same system. Well, original PCs weren't designed for that. They were designed for one user, okay? But as technology developed and networking developed, they realized that even personal computers could benefit from multiple user interfaces, right? So that every user gets their own sort of features to it. The newest versions of Microsoft Windows does this, from Windows 8, which is, I know, a little bit buggy. But one of the things that you find that's neat about Windows 8 is when you log into a new Windows 8 computer, it picks up your settings. Like all of a sudden your desktop is there and all your applications, or at least the shortcuts to them, are there. That's even more of the advance now of the multi-user systems, okay? So as a result now, the problems of time sharing and communication had to get tied into this type of networking technology, okay? OSs are also responsible for all your peripherals. So whether it's mice, keyboards, the simple ones, to printers, scanners, other types of peripherals, the OS is responsible for that. This is often done through what's called a device driver. A device driver is just a piece of software that connects the device to the OS. Here's where systems like Mac, the Apple software, has an advantage, because they know generally what most of their peripherals are going to be because they build them. Right? They build the hardware so they know what their peripherals are. Where Apple has a problem is if all of a sudden we want to plug some other company's hardware into their system, they're like, hey, what is this USB? This is not an Apple USB. How am I supposed to read this thing? Well, in order to read it, it needs some driver software. Now, if it's a USB, that's not too bad. You can sort of figure that out. If it's something more complicated, like a new keyboard you want to plug into the Mac, then it needs more driver software, and the Apple OS has to be able to handle that. This is where a system like Microsoft, in a way, had even more work to do. Because Microsoft just made software, it didn't make the hardware. So when it made that software, it had to be able to work with any hardware, right? Like, oh, IBM's going to build it. No, Dell's going to build it. No, Acer's going to build it, right? They had to be able to pick up all that. So then what we try to do is come up with sort of common protocols for these drivers to work, okay? But it doesn't always work that way. All right. Lastly, some OSs need to support real-time systems, okay? Now, this wouldn't be a personal computer, not necessarily, but this would be systems like healthcare systems where you need that immediate response, or banking where you can't have, like we talked about the ATM example last time, where you must have a minimum response time to actually work the system in real time so that we can't cause some sort of massive error in the system itself, okay? So critical time management systems like hospitals, banking, or nuclear reactors, right? We don't need to have the spinning circle if we're running a nuclear reactor. We need immediate response time. Okay, memory management. So the OS needs to track remember processes are apps, track the processes that are in memory. So OS needs to know what it's running, right? It needs to know what are all the apps I'm currently running. It needs to convert those processes into actual memory, right? So it goes, oh, I want to run Word and Chrome and Excel at the same time. So I need to specifically block out memory for those three programs so they know, their code knows what memory they have access to, okay? So processes would contain things like, oh, these are the variables you're going to use in your software. These are the class objects. These are the method calls, etc. So it blocks out a piece of memory for one process and another for another. Now, it's not always even, right? It's not like every process, every app, needs the same amount of memory. That's something it has to figure out, right? Okay. So a logical address, sometimes called a virtual address or even a relative address, is a piece of memory that has a specific location relative to the process. So the process, say Microsoft Word, is connected to this address in memory. But it's not relative to main memory, okay? A physical address is the actual memory address, okay? When you run or compile your process, a reference to an identifier, like a variable, is changed into a logical address. So this is where your code starts to become real. So in your code, you might have a variable. So when it compiles your code, it turns that variable name into a piece of memory. And that's the way, when I first taught you guys variables, I would draw a little box. So the box is the actual address. So it's turning your code into actual memory addresses, okay? Eventually, this will then get loaded into physical memory, okay, where the logical address is translated into a physical address. Again, I don't think the IB curriculum goes into that level of detail, but I just kind of wanted to lay that out for you. So you have to think, again, the actual hardware keeps track of a bunch of memory addresses. And in there is going to be a bunch of ones and zeros, which we know could be anything. That could be a number. It could be a letter. It's really a number, but it could be a letter that the number represents. That's what we were talking about in the last unit, okay? There's a process there called binding that's occurring, okay? The binding of your code identifier to a physical memory address is called address binding, right? So you are connecting your code, which is this thing you wrote in a coding language, into actual physical memory by binding them through address binding, okay? Okay. So let's start by assuming that we have two processes, the operating system and one app running, okay? So we're going to run a very simple system here, an operating system and the app. And we have all this memory to use. Well, obviously some of the memory has to be for the operating system itself. And then maybe the rest of it can be for the app. Say the app is a game, okay? So what we'd want to do is not necessarily divide it 50-50. We'd want to figure out what does the OS need and what does the app need, okay? Okay, to bind the addresses, we need to know the account of the OS, make this very simple, but at the same time limit the amount of apps we could run if we want to maximize the amount of memory being used by the OS versus the app. And you don't see this too much in modern computer systems. It tends to allow you to run as many apps as possible. But in older systems or different types of computing systems where they don't allow multiple apps, this is what they do. They say, well, we need this much memory for the OS, and you want to run this app? Okay, you can run it. Oh, you want to run 2 apps? Nope, no memory for that. You got to just run the one, okay? So once we move into multiple processes, it's the job of the OS to lay out the memory, okay? So there's 2 strategies it can take for this, okay? One called a fixed partition technique. It divides the main memory up into partitions. It says, you're going to have this much memory, you're going to have this much memory. Not necessarily the same size, but it divides up the memory for the OS and the apps that are needed, okay? And then we have what's called the dynamic partition technique. Dynamic, just like a dynamic data structure, changes the memory as needed, okay? So what's the advantage versus disadvantage in you guys' opinion? So I start my operating system and I want to run 2 apps. Should I just carve out equal memory for both of them and just say that's how much memory you get? Or do I allow the memory to be flexible depending on which app needs more? First of all, what's the advantage of fixing the amount of memory? Yeah, easier for it to manage, absolutely. What's the disadvantage of a fixed technique? Yeah, the app might need more memory than it's allowed at that point. What's the advantage of a flexible or a dynamic partition? Yeah, so the apps have the advantage. What's the disadvantage from the OS's side? Yeah, less control, and it has to manage it more, right? So the OS has to do more. If it uses fixed, it just goes, there you go, there's your memory, I'm going to leave you alone now. If it's dynamic, it's got to be watching all the time to see who needs more memory. So always with this stuff, there's advantages, disadvantages, and those are the kind of questions often the IB asks. What are the advantages? What's the disadvantages? So be ready to answer those types of questions. I don't think they're going to go into this detail, but it's there, okay? So for a technique to work, the process must fit into the partition allowed, okay? As I just said, fixed partitions are easier to manage but restrict the opportunities of the process. Dynamic partitions are more flexible for the apps but more to manage for the OS. And then we have the page memory management technique, which again divides it into fixed blocks called frames and then divides those frames into pages that fit into the blocks. You may start to notice something here from, depending on which thing you went to in the Prairie DevCon. Some of the now programming language is starting to match up with this. I can't remember which one it was using the terms frames and pages now. Did anyone attend that event? I think it was for programming for Android. Android's OS now is starting to use those words in how it manages apps in the system. So it's kind of neat that that's starting to come around there a little bit. Okay, again, I'm going into a level of depth here that I don't think you guys need, but let's just sort of skip ahead here. In demand paging, pages are brought into memory on the demand of the process. So if the process requires more memory, a page will be brought into memory from secondary memory from an available frame. So this idea of frames and pages is just a system of managing the memory, okay? This is also related to virtual memory. This idea that there's more memory available when really there isn't by just using some of the hard drive space to create a virtual memory, okay? The use of virtual memory, though, can cause a slowdown in a technique known as thrashing, which is that the fact is that physical memory, like hard drives, is slower than like RAM because it's a spinning device, right? Okay, process management. So to manage these processes, okay, here's the way it works. Okay, so you want to launch your app. So the app process is created in a new state, okay? If the process has no memory barriers, then it's said to be ready, right? The app is in a ready state. Then once it's past the ready state, it goes into a running state, okay? If that running state requires access to resources that may or may not be available, then it's in a wait state, okay? So for example, if it was a really intense game and it might require more memory, then it's in kind of a waiting state. And then when you're finished running it, it goes into the termination state. So these are the states that an app can be in. And again, if you get into programming for Android, you're going to start to see some of this terminology right in the code you write a little bit. Okay? Okay, so here's a bit of a diagram that kind of tries to explain it. Okay? So you go to launch a new app. So it's put into the ready state. Okay? Then, if you can get this app up and running right away, it'll dispatch it to a running state. Now, it's possible that while it's running, something interrupts it. If it interrupts it, it gets put back into a ready state. So say you had a game running, and then all of a sudden something popped up, like Skype. Your game is put back into the ready state. As well, your app might, like say it's, classic example, Chrome. Chrome lately is a real nasty memory hog. So all of a sudden, Chrome, which was running, is put into a waiting state because it's waiting for memory to free up, and then gets put back into the running state, right? Actually, no, it doesn't get it's put back into the ready state, and then put back into the running state. Then finally, we shut it down, it gets put into a termination state. This is pretty common sense stuff, but again, you have to kind of think of it from the computer standpoint, that it has to manage your apps in this way. It has to kind of think about it that way. If it didn't have a waiting and ready state, if it just went from you start the app, it runs, and then it shuts down, we couldn't have multitasking, right? We couldn't have two tasks running at once. We couldn't interrupt one task with another unless we had a place for that app to wait for the other app to get going, okay? Or to be ready to go. Okay, so here's again some more specific details. That there's something called a process control block, okay, or the PCB, which moves the states around, and it keeps a track of it with a counter that keeps track of where it is. And I believe I have a diagram for this coming up, okay. As well, they have these ideas of preemptive versus non-preemptive of the terms of the state. And then they run algorithms on this, like things like turnaround times. Operating systems are really complicated software. Probably the most complicated software you can write, okay? This is why they don't come out all the time. And this is why you have to have a big company to write an operating system. It is not an easy thing to do. Now, if you go and study this at the university level, they actually have courses in operating systems that are really complicated, just sort of the groundworks of how to write basic operating systems. Because that happens a lot, right? There are companies that write basic operating systems for simple devices, often the hardware they make. So let's say you come up with a new Roomba, a new vacuum, a new robot vacuum. You might want to write your own OS to control that yourselves. I mean, some of you guys did that robot competition with the vocational. You were using somebody else's OS to do that. If you can write your own, that's kind of powerful, but you have to maybe start thinking about some of these things depending on how much you want that OS to do. Okay. So a first come, first serve approach moves processes from the ready state to the running state in the order they got there. So this is basically a queue. First come, first serve. So just like a queue, as we start launching apps, it puts them into a queue and says, okay, you're in the ready state, now I'll move you to the running state. But you got to wait because this guy's running right now. Okay, now I'll move you into the running state. And this chart shows process times according to the CPU in term. So say I had 5 different apps running, or 5 different processes. So this app would require 140 units of time versus 75, 320, 280, 125, right? Here's the chart down here that kind of shows it. So from the time 0 when I started the first process, it took 140 units of time before I could then start the second process to move it from the ready state to the running state. And you know this too. Some apps start slower than others, right? But on average, if we took these 5 apps, the average time is 529, okay? So sometimes when it looks at this, it thinks about the running apps and then the average time it requires to run these, okay? And it might think, what's the fairest way to run these apps? Not the So first come, first serve may not be the most fair way to run the apps, okay? What it might then do is go, okay, this user wants to run 5 apps. I should put them in order. I should run the fast ones first So I'll run P2, then P5, and this long one, P3, I'll run it last because I know it's going to take the most amount of time. So this would be a classic example of a sorting algorithm, right? Where a sorting algorithm could relate to the actual physical hardware, where I say throw all these apps into the queue, and if I went first come, first serve, then it's just going to run this one that takes 320. P4 is going to have to wait a long time before it can run, whereas in the other system, P4 runs fast, runs earlier because it's going to take less time to get started, right? So this is the kind of stuff that an operating system needs to do. It needs to analyze apps and running times and kind of come up with a fair system for running it. And this is hard. This is why even operating systems like Windows 8 that have come out don't necessarily do a good job at this, because it's hard to do this sometimes. And sometimes you don't know if this is going to work until your operating system is just actually up and running. And then you get a feel for exactly how it's going to work that way. Now, another way is a round-robin approach, where it goes, you know what, I'm just going to slice off equal amount of time for each of the apps and just divide it up. So I'll go, okay, I'm going to start P1 for a little bit, then I'll start P2 for a little bit, then I'll start, and again, it's going to start running through your code. Now, this will work well if you have, say, multiple processors. So you can start sending out the processes to different processors, right? But again, it depends on the hardware there. And that's it. Now, before we wrap, let's go back, all the way back to the beginning. And after having thrown a lot of those terms at you, let's re-examine what the IB curriculum said you should know for this. Okay. Identify the resources that need to be managed within a computer system. Primary memory, disk storage. Okay, that was a pretty easy one. Evaluate the resources. This could include mainframes, PCs, laptops, etc. Identify the limits of a computer system. For example, single processor may not be able to handle graphics better. Describe the possible problems from a system that is limited. For example, what if the primary memory is too small? What if the speed is too slow? So far, this is pretty simple, okay? I think from this point, looks good. Now, moving to the next page, it gets a little more technical. The role of the operating system in terms of managing memory, peripherals, and hardware. So it says, for example, allocating storage, keeping track of programs in memory, swapping between programs on time slicing, and priority when one is waiting for input. So this would be the idea of, again, this is just the example here. Outline OS resource management techniques, scheduling, policies, multitasking, virtual memory, paging, interrupt, polling. Technical details will not be required, but it is expected that students will be familiar with these techniques and understand when and why they're used. Okay? Discuss the advantages of producing a dedicated operating system for a device. Advantages to size, speed, customization should be considered. For example, a dedicated operating system for a cell phone rather than using a pre-existing operating system. Okay? Outline how the operating system hides the complexity of hardware from users. Students should be aware of a range of examples. For example, drive letters, virtual memory, input devices, the Java virtual machine itself hides that from the memory, etc. Okay? And that is what that was about.